Hello guys, welcome once more to Prepclass Physics class online, and my name is Tutor Dami. In this edition, we are looking at Waec Physics 2016, questions 16 to 20, and we shall be dealing with those questions and making it something you can do. In this edition, we are looking at questions from expansivity, that's expansion, expansivity, and we are looking at questions from different difficult aspects of physics that many students say are difficult, like temperature scale. Now, most of those questions are very easy, and we shall be proving that to you in this edition. Don't forget that if you learn anything from this video, click on the like button. We have more content to share with you that will better help you understand physics. Now let's check out number 16. In the clinical thermometer, the function of the kink is to what? Now you have the kink. You've seen the thermometer before. The kink is the part of the thermometer that is actually, if I say that, I'll be answering the question. Now, A, prevents the backward flow of mercury after use. Ensures the backward flow of mercury after use. Maintain the thermometric property of mercury. Allows the temperature attained to be read. Do you have any idea what might be right? Now, actually, if you don't know, I'll tell you. Now, first of all, I'll use a picture to explain that to you. This is a thermometer. This is the constriction. That constriction is also called the kink. So the kink is the one. Now, the function of this kink majorly is that when you are not measuring any temperature, the mercury, that's this red substance, the mercury stays in this bulb. The mercury stays here. That you are not measuring any temperature. So it's not increasing, it's not decreasing, it just stays at the bulb here. Okay, now, but when you are measuring temperature, it flows out. So this kink prevents the mercury from moving anyhow, both up and down. So the kink helps to, it's like a lock. It helps to prevent the mercury from flowing forward and backward. And when you finish reading, if there is no kink, it will just flow back. Like if I read my temperature as, let me say, 37 degrees Celsius, and there is no kink, there is no stopper here. If there is no kink here, the mercury, as I finish reading it, before I even check it or look at it very well, it will have flowed down because there is no stopper. But kink acts as a stopper, so that the mercury will not flow too freely and will not give us challenges with taking temperature. So the function of the kink is to, one, prevent the backward flow of mercury after use. Does it ensure the backward flow of mercury? Does it make mercury flow back? No, it only prevents it from flowing back immediately after use. It takes a while for the mercury to rest back again. So the kink stops it, it locks it and makes it difficult. So because if the mercury flows back immediately after use, then you can't take readings. It has to stay for a while before it flows, and that is the work of the constriction or the kink. And that is it. Now, ensures the backward flow. It is not the kink that makes it flow back. It is gravitational pull that makes it flow back. So 2 is wrong. Now, maintains the thermometric property of mercury. Is it the one making mercury to respond to heat? No, it doesn't affect mercury. It has nothing to do with the mercury. Mercury is naturally thermometric on its own. So that means it responds to heat. That means it expands when heated. So that means it can perceive heat and expand and show you reading. So it is not the kink that makes mercury mercury. Mercury is naturally a good boy on its own. So now the last one says allows the temperature attained to be read. Kink make it possible to read temperature, and that's because it prevents the mercury from flowing back immediately. So you can still hold it and still see what it reads. Oh, this is okay. It is still there because of the kink, and that is the answer, and that is correct. So the answer is therefore option 1 and 4. It prevents the backward flow of mercury after use, that's immediately, and it allows the temperature attained to be read, and that is also true. Those are the true answers to that question. Let's check out number 17 now. Which of the following statement correctly defines the boiling point of a liquid? The temperature at which what? What happens at boiling point? Can't define boiling without measuring saturated vapor pressure. So these options C, D, and B, C, D are wrong because they never spoke about saturated vapor pressure. Now, boiling point is the point where what happens at boiling point? It is the point. It is simply defined. In fact, it is defined as the point where liquid the saturated vapor pressure of the liquid is equal to the atmospheric pressure. That is the perfect definition of boiling point. It is a point where liquid change to vapor, and the reason is because the saturated vapor pressure of the liquid is equal to the boiling point and is equal to the atmospheric pressure, and that is boiling. Like now, look at this now. This is unsaturated because the vapor here is escaping. Okay, this will take longer time to boil, right? Now this one will boil faster, and the reason is because you've covered it. So this is the saturated vapor here. And why is it called saturated? That means the vapor here is charged. It is like liquid, because at this point all the vapor, you will see that the top of the pot will be wet because there's enough vapor here which is equal to the vapor here. So the pressure inside the boiling water is equal to the pressure around here. So we see that here is saturated vapor. It has the same pressure as that which is here. So that means as the water is boiling here, the amount of pressure here is equal to the one happening here. That means this place is as charged as the inner part of the pressure. So the inside, the entire system here is saturated, and we call it saturated vapor. But here it can't be saturated because it is escaping. So it is getting lower and lower and lower and lower. So it can't. It is just losing it. So the system is exothermic. It is losing it to the environment, right? Now, but a point will come when the vapor pressure of the liquid will be equal to that of the environment, and then the liquid will start to boil. It will begin to boil and boil and boil and boil. So boiling happens when the vapor pressure around in the atmosphere equals the vapor pressure of the liquid, and that is what causes boiling. So the answer is therefore saturated vapor pressure equals the atmospheric vapor pressure. That's the one in the atmosphere is equal to the saturated vapor pressure of the liquid, and that's what causes boiling. And that's the answer for number 17. Number 18 says the diagram is used to determine what? Do you have any idea? Now, if you don't know, I'll tell you. Now, first of all, you must know that this is an ipsometer. It's an ipsometer. This is an ipsometer. It has a manometer here, and it has a steam exit here. Now, this is used for what? It is used for only one thing, to determine the maximum steam point of a thermometer. You know, thermometer has 2 points. It has a lower fixed point, and it has a upper fixed point. Like if you have now for example now, water boils at 100. That's the maximum, right? That's the upper fixed point for water. But water freezes at 0 degrees Celsius, right? That's the lower fixed point. Now, how can you know what is the maximum fixed point of a thermometer? If you are building a thermometer, how will you know where to put your 100? And how will you know where to put your 0? You need an ipsometer. An ipsometer helps you to determine where your 100 mark will be. And here we have boiling water now. Now, as the water is boiling, you know, water boils when the atmospheric pressure, like I said before, when the atmospheric pressure is equal to the saturated pressure of the liquid. So that's what the manometer is watching. This manometer is gauging the pressure, because pressure is also a function of water. That means boiling water is affected by pressure. That's why if you cover your pot, the water will boil faster than if you open your pot, because there is more pressure when you cover your pot. Why? Because the steam or the smoke is not escaping freely. So if you cover your pot, it will boil faster. But if you open the pot, it will take longer time to boil, and that is just it. So the pressure affects boiling. So that's why we have a manometer here. You know, manometer is used for pressure. Then we have here steam exit. As the water boils, it can exit also through this steam exit. So this is used to measure the maximum or the highest temperature scale on this new thermometer. Now I have a new thermometer. I don't know where I will put my 100, so I can always know by the ipsometer. It will give me the guide of the maximum point. That it will show readings on this thermometer where the maximum point will be when this water boils. So I'll now know where to put my 100 degrees Celsius mark on the new thermometer. And this one is used for cooling. It's for knowing where to put your 0, because 0 degrees Celsius happen when the water is changing to ice. So this will show you that, but this is not the focus of this question. So our focus is on the ipsometer, and that is what we have here. So it is used for finding the upper fixed point of the thermometer. Full stop. And let's check out number 19. 1966, an aluminum rod of length 1.8 meter at 10 degrees Celsius is heated to produce a difference in length of 0.007 meter. Calculate the temperature at which it is heated. Now, linear expansivity of aluminum is 2.3 times 10 per mouse 5 per Kelvin, right? Now, this is a linear expansivity question. So I'll just, you know the formula, right? Now, the formula of linear expansivity is linear expansivity equals change in length over length times temperature 2 minus temperature 1. Now, that is linear expansivity. And in my question, my linear expansivity is 2.3, right? Times 10 raised per minus 5. My change in length, the difference or the extension of length is 0.007 meter. And then my initial length is 1.8 meter. They are all given to me in the question. Then my initial temperature is what? 10 degrees Celsius. So I'm to find my final temperature, and that is the one I'm looking for. So the first thing to do is to manipulate the formula. That means turn the formula upside down. Make theta 2 my final temperature the subject of formula. Now this is the formula for linear expansivity workings in physics. This is the formula for anything linear expansivity in physics. But now I'm to make this final temperature, that's theta 2, the subject of formula. So first of all, I will cross multiply. That will be giving me this one will come here. We'll multiply. That will give me linear expansivity, that's this, times length times temperature 2 minus temperature 1 equals change in length, right? Now I'm to remove everything except my temperature 2. So now first of all, remove expansivity and length. That they will come below. So that will come temperature 2 minus temperature 1 equals change in length over linear expansivity times length. Now I'm to find my temperature 2. So I will remove my temperature 1. It will move over here and become positive. It will become change in length over expansivity times length plus the temperature 1. And that is it. Now plug in the value. So I have 0.007 over 2.3 times 10 to the power minus 5 times 1.18 plus my 10. So first of all, begin by multiplying the ones below, then divide the one on top by the one below, then plus 10, and that will give you 179 degrees Celsius. I say it again. First of all, begin by multiplying the one below, then divide the one on top by them, then plus 10 to the answer you have, and you will get 179 degrees Celsius, and that is your answer for that question. The answer is 179 degrees Celsius, and that will be your final temperature at the end of that linear expansivity experiment. So that is the answer. Don't forget the linear expansivity formula. It is super important. Let's check out number 20. A mercury-in-glass thermometer reads 4 cm at ice point and 29 cm at steam point. To calculate the temperature at which the mercury level is at 9 cm. Now, what will be the temperature in degrees Celsius? Now, all thermometric questions, that's all questions that have to do with thermometer, can be solved in only one way, and that one way is this. Now you know we have the maximum point, that's the steam point. The lowest point is the ice point, right? Now this is my ice point. This is my question here. 4 is my ice, 29 cm is my steam. Then in between is 9, right? Now find what will that 9 be in degrees Celsius. Of course, my 29 cm is my 100 degrees Celsius. My 4 cm is my 0 degrees Celsius. Now, what will be my 9 cm in degrees Celsius? That's what we are finding now. So the first step is to say x minus 0 over 100 minus 0. That's the method to solve any question on thermometer. Then 9 minus 4 over 29 minus 4. And that's what I have here. This is the first step. Now 9 minus 4 is 5. 29 minus 4 is 25. Then cross multiply. So 25 will come to x. And then 5 times 10 will, times 100 will form 500. Then dividing by 25, x equals 500 over 25, and that is 20 degrees Celsius. And that is my answer. My answer is 20 degrees Celsius. And that is the end of this. Now, don't forget that this method can teach you, this method here can solve any question on thermometer. And that is very important for you to remember that. Now, let's see. This video to the end of this video. Don't forget, if you click on like button, we have more content to share with you that will further help you understand physics. Until we see next time, guys, take care of yourself and bye for now.